Great. So in the last chunk, we talked about some theory behind the k-means algorithm and how we could view it as optimizing an energy function in this coordinate ascent type of way. In this little chunk, we're going to talk about some problems which the k-means algorithm has. And in order to sort of kickstart us, I want us to think about running k-means to convergence on the following data set. So we've got exactly the same k-means algorithm we've been looking at before on the right-hand side here with the initialization, assignment, and update steps. And on the left-hand side, I've now got a new data set. So this is a different data set than we had before. And the data set has a cluster at the top here that we might like to identify that's roughly spherical in appearance in X space. We've got this cluster down here, and then we've got this more awkward looking, thinly stretched out cluster in the middle here. And what I want you to think about is, where will k-means converge to when it's run on this data set? Ideally, we'd like the type of solution I've shown sketched out rather poorly with my pen, but will it actually find that clustering solution? And to make things a bit easier, I'll show you an initialization. Okay, so here's a concrete initialization of the k equals to 3 clusters that we're going to look to assign data points to. The red, magenta, and blue points on this diagram. So I want you to pause the video and think for 30 seconds what you think the likely clustering solution is going to be and whether that's going to be a satisfactory solution to this problem. Great, so hopefully you've done that. And now let's run the algorithm forward from this point and see what happens. So here's the first assignment step. You can see that the red cluster picks up big chunk of that middle selection of data points. The blue one looks like it's grabbing stuff towards the right, and the purple one stuff towards the bottom left. So all looks hunky-dory so far. Let's update the parameters of the clusters. In the update step, we take the means of those collections of points, and things are looking pretty promising. The red and magenta things are bifurcating and going to the top right and bottom left, respectively. Let's do another assignment step and iterate. And we're going to keep on running this backwards and forwards between assignment and update steps. Things are looking like they're starting to settle down. The allocation is not changing too much now. And if you look at the updates are starting to be imperceptible. You can't see the little lines drawing the old cluster center and the new one. Let's carry it on, make sure we really have converged, but it's not looking brilliant. Okay, at this point, the allocation has not changed, the assignment set has not changed, and you can see that the blue cluster has gone and grabbed those data points from the middle cluster that were closest to it. And similarly, the magenta cluster has also grabbed those red data points that were closest to it. So something has gone wrong. And in this case, this is not a problem to do with initialization. So you can rerun this thing a bunch of times. You can even try a really friendly initialization where you initialize the cluster centers to be bang on where you'd like them to be. And you'll find that these clusters on the outside always go and gobble these regions of the middle cluster that really you'd like the red cluster center to pick up. This is not an ideal solution because it seems pretty clear by eye that the red middle cluster should have been a long, thin cluster, and it shouldn't have bits which are gobbled by these disjoint clusters on the outside. And the question is what to do about it. Initialization doesn't solve us. We can't hope to look for a better initialization. One thing that could solve us is going into this distance measure in here, and we could fiddle with it. And in particular, one thing that might work in this example is to change the way different dimensions are weighted. So for instance, if we put greater weight on distances in the vertical direction, so you paid a greater cost for distances in the vertical direction than in the horizontal direction, or vice versa, we could ensure that all of these points are close together and all of these ones are close together. So introducing a weighting factor through each of the dimensions here could solve that problem. That feels like a little bit of a bespoke solution that won't generalize to other cases. because I could imagine perhaps even more pathological examples like the following. So we might have some clusters which are skinny and thin, and other clusters which are tall, and we might have things which are perhaps correlated and other ones which are other shapes. So we can't really manipulate this distance measure in a way that would take into account situations like this. So although toying with the distance measure and perhaps having horizontal distance carry less weight than vertical distance is one solution to the problem that would work in this specific case, in this more general case, we're not going to find a distance measure which resolves our problems. So the k-means clustering algorithm, as written down at the moment, is going to really struggle when different clusters have different shapes. So that's one problem. A second problem, which is kind of related to this, is do we really want a hard assignment of data points to clusters? So for instance, these data points here that were misclustered, wouldn't we rather say that they were sort of, were kind of uncertain as to what cluster they belong to in this case? I mean, it's one thing grabbing them into the blue cluster over here, but if we said we were sort of uncertain about those data points, maybe we could say we're really certain about these ones, but these ones, we're not sure. We think they should belong to the blue one, but maybe there's a chance that they belong to the red one. Maybe then at least downstream applications that rely on our clustering would be able to sort of flag those points up and as ones we should pay particular attention to. So in general, there's a question of whether we do want hard assignments. This is giving us hard assignments here in this step. Do we really want soft assignments? Maybe soft assignments would enable downstream applications to detect misclassified points more easily. They're often the ones that you're uncertain about, and do something special with them. If you're in medicine or something like that, where you've clustered a patient to a particular subject group, you'd like to flag up uncertainty to the doctor before that they sort of blindly went ahead allocating treatments or something like that. Okay, so that's a couple of pathologies with the k-means algorithm that we might like to avoid. The k-means algorithm, taking a step back, produces very strange results when clusters have different shapes. They return hard assignments, and soft assignments in some applications might be more sensible. And initialization in general, as we talked about in the last chunk, is a bit delicate. There's a really good algorithm called the k++ means algorithm, which takes care of the initialization problem to some extent. It has theoretical guarantees, and it tends to produce really good results. And the basic idea is that the cluster centers get initialized by selecting data points. So you initialize them to specially chosen data points, and you tend to try and choose data points which are spread out through the space. So you try and spread your initial cluster means out across over the space, and that can actually provably give good results and find good, still local optima, not guaranteed to get global optima, but good local optima of the cost function C. So in the next part of the course, the next few chunks are going to try and address these first two problems, having solved the first problem with, the last problem with the k++ means algorithm problem. And the way that we're going to do it is by talking about probabilistic models, and in particular, mixtures of Gaussian models. So in the next chunk, we'll start talking about mixture of Gaussian models and how we can use learning and inference, like we've touched on in other parts of the course, in order to solve these two key problems with the k-means algorithm.